So hopefully, I guess I didn't scare everyone away with all of the math in the previous lecture. So this is lecture 2 of my 3-lecture sequence. And this one is all about random number generation flaws. And I promise there is less math in this talk than there was in the previous one. So the sort of motivating question for all of the work that I'm going to talk about in this next hour and a half is sort of the question of what does cryptography look like on a broad scale? And our methodology for this research is sort of a 2-step process. One is collect cryptographic data. This means sort of keys, signatures, ciphertext, whatever we can get in cryptographic usage in reality, and then look for interesting things, mostly things that should not be happening. So here's our project. So step 1 of this project is getting data. Fortunately, there's a lot of cryptography out there that we can look at. So of course, the sort of, I think, canonical example of a public key infrastructure that we use every day in practice is HTTPS. And so in HTTPS, secure HTTP, the public keys are used to essentially bind domain names to certificates so that you're assured that you're actually connecting to the website that you really want to connect to. Keys are also used to sign certificates for self-signed certificates, or if your certificate is signed by a certificate authority, they use their key to authenticate your certificate. In the most common case for HTTPS, the public keys are also used to encrypt session key information. Almost all of the HTTPS servers out there use what is known as Rsa Key exchange, where when a client connects to a server, the client gets the server's public key, generates some session key seed information, and encrypts it to the server's public key and sends it back to the server. And then they both agree on the same session key because the client generated it essentially and sent it to the server. This is the most common case. And this means that if we compromise some HTTPS keys, they could be used to man-in-the-middle connections, because someone with a private key for TLS certificate would be able to sign the session just as if they were the real server. And in the case of Rsa Key exchange, it's not forward secure, so an attacker with a private key would be able to decrypt passively collected session traffic, because they could just decrypt the session key that was sent from the client to the server and just then decrypt all of the following traffic. And if a CA key was compromised, it could be used to sign new trusted certificates. So this is sort of the security and threat model for HTTPS. Then, of course, the question is, how do you collect HTTPS data? In 2010, the EFF published a database of SSL certificates, the SSL Observatory, and they got this data by doing a scan of all of IPv4 on port 443. This took several months, and they got several million certificates. So I guess they found 16 million hosts with an open port, and successfully retrieved a certificate from, I guess, 7.7 million of these hosts, and that gave them 3.9 million distinct Rsa keys and a much, much smaller number of Dsa keys. So Rsa is the standard public key algorithm used for HTTPS. And I'm going to talk about a lot of results from this paper that was already mentioned, which was done with Alex Halderman and a couple of his students, Zakir Durumrich and Eric Wustrow. And when we started this research, we actually repeated a similar scan to the EFF, and we did this in October 2011. Similarly, we used a fair amount of computing resources to essentially nmap the entire internet, download all of the certificates that we could find. In our case, we did it from, I guess, 25 Amazon EC2 nodes. And here's some of the numbers that we got for the number of certificates that we got. So we found a few more certificates and keys than the EFF did, but the numbers are about the same. And in his talk on Wednesday, Alex will talk about how to do this kind of a collection much more efficiently. So without needing to spin up 25 Amazon EC2 nodes. Another example of public key usage in practice that many of you probably use every day is SSH. In SSH, host keys are used to authenticate hosts to clients. So in this case, I'm only going to talk about host keys because these are the ones that are easy to collect. A compromised SSH host key could be used to man-in-the-middle connections. Essentially, in SSH version 2, the most common case, the client and server do a Diffie-Hellman key exchange, and then that's signed. The server uses its host key to sign the key exchange in order to authenticate itself. That's when you're asked to verify the fingerprint. And so if an attacker were able to compromise an SSH host key, they would be able to sign, they would be able to do the key exchange with you and sign as if they were the real server and man in the middle you that way. So in this same paper on weak keys, in addition to scanning HTTPS hosts, we also scanned for SSH host keys and handshake signatures in a couple of scans in 2012. And we found actually similar numbers to HTTPS. So we successfully completed 10 million handshakes, got 3.8 million distinct RSA host keys and 2 million distinct DSA host keys, and a much smaller number of elliptic curve DSA keys. And interestingly, there are also a few hosts out there using GOST, which is a Soviet cipher suite that is almost exclusively used in Russia. One thing that's interesting about these numbers, the number of distinct keys is much, much smaller than the number of successful handshakes. And almost all of these keys, basically most of the SSH servers out there support both RSA and DSA host keys. So these are overlapping. These are almost all the same hosts. So not very many distinct keys out there for the number of hosts. Another sort of canonical example of a public key infrastructure that you might want to look at if you're thinking about investigating cryptographic use in practice is PGP. So PGP keys are used to sign and encrypt email messages. A compromised key could be used to decrypt messages intended for that particular person, or sign messages or other keys as the person who owns that key. PGP public keys and signatures are available on public key repositories. And there's several PGP key repository dumps available online. If you want to start your own PGP key repository, you can just download one of these dumps, start syncing with other key repositories, and serve keys in your own personal repository. So if you want to analyze PGP data, all you have to do is download one of these dumps. And if you could also set yourself up to sync, but downloading the dumps is easy enough. So here's some statistics from a PGP key repository that I played with at some point last year. There were 700,000 RSA keys, 2.1 million DSA keys, and 2.1 million Elgamal keys. In a paper that was published at a similar time as our paper on weak keys by Lenstra and a number of other authors, they analyzed the PGP data. They also analyzed the SSL observatory data in addition. Another sort of interesting example of public key infrastructure especially sort of in the past year, is Bitcoin, so the decentralized cryptocurrency. Bitcoin uses elliptic curve DSA, and the security of Bitcoin, of course, relies on this. A compromised Bitcoin key could be used to transfer Bitcoins from the compromised account. Essentially, your Bitcoin address is your public key. And the blockchain of Bitcoin transactions is signed by people's Bitcoin keys. And so you have keys and signatures. And as part of the protocol, all of the clients who use Bitcoin, they download the blockchain when they connect to the network. This is what allows the decentralized property. And so this means that if you want to analyze Bitcoin, you can just sync yourself into the Bitcoin blockchain and download all of the keys and all of the signatures. And in order to make this process easier for new clients, there are many places where you can download the blockchain in bulk, and you can just find one and download everything and start analyzing. A couple of people, Jonathan Moore and Eric Wustrow, looked into this earlier this year, and also Schneider. In January, there were 187,000 keys and 23 million transactions in the Bitcoin blockchain. The last example of a public key infrastructure that I'm going to talk about is some national ID smart cards. There are many countries that are introducing smart card IDs in order to have sort of, sort of digital country. Taiwan is one of them. There are many other countries. I'm going to focus on Taiwan. So the national public key infrastructure that Taiwan is adopting, Taiwanese citizens can use their smart card IDs to file income taxes online, do things like update their car registrations, do transactions with government agencies, apply for grants, interact with companies all online, so they can use their cards for authentication and also for encryption and to provide legally binding signatures. So in March 2012, some Taiwanese researchers collected 3 million certificates, all using Rsa keys from the national LDAP directory. This directory had 2.3 million distinct 1024-bit RSA moduli and 700,000 2048-bit RSA moduli. So these are essentially from just 2 generations of cards. And we analyzed this data in a paper which has not been put online yet, but will be shortly. So at this point I want to talk about what could possibly go wrong. So cryptography relies on good randomness. And if you, for some reason, use predictable randomness, an attacker might be able to predict your private key. End of story. Is that the end of the story? Once we have all of this cryptographic data, you can think, okay, what could we possibly look for that would be interesting? The sort of simplest thing that you might think to look for in this data is repeated public keys. So theoretically, 2 parties should never share the same public key. If they share the same public key, they have the same private key, they can do all sorts of terrible things to each other. But if in the theoretical model, everyone generates their keys uniformly at random from some distribution, nobody would ever share the same public key and everyone would be secure. So what do I mean by repeated keys? Well, in the case of RSA, remember that an RSA public key is the modulus n and an encryption exponent e. It is not a problem for 2 different entities to share the same E. In fact, almost everybody uses the same few values of E. This is a plot of Ssl certificates, the E values that are being used. Note this is on a logarithmic scale. So almost everyone uses this value 65537, which is 2 to the 16 plus 1. And there's a few other, mostly tiny values that are commonly used, like 3, 5, 7, 11. But essentially, there's almost no variation in the exponent used. If you visit a random website and look for the exponent, it is almost certainly this value 65537. It's also worth noting that essentially nobody uses particularly large values of E. Everyone uses very small values of E. Sharing E is not a problem, but of course sharing N is a problem because if two parties share the same N, N has unique factorization. They both have the same private key, and this means that they can decrypt and sign for each other, which is not what you want out of your public key crypto system. A slightly more subtle problem than sharing exactly the same N is, what if two RSA moduli share exactly one common factor? So they have the prime factor P in common, but they have different second factors Q1 and Q2. The security implication of this is that an external attacker, so me, I know nothing about these two parties. If I compute the GCD of the two RSA moduli N1 and N2, it will be this common factor P, and that will let me factor each of these keys just by dividing out by P. The reason that this is significant is that from a running time perspective, I mean, we saw in the last lecture how much resources it takes to break an RSA key just outright if you want to factor the hard way. The current record is a 768-bit RSA modulus that took 2.5 calendar years from a bunch of academics running supercomputers. The amount of time that it takes to compute the greatest common divisor of two 1024-bit RSA moduli is about 15 microseconds on my laptop. So this running time, this difference in running time means that this, if it were to for some reason happen, would be a significant vulnerability for RSA. We also saw a large number of Dsa keys in practice. So what could happen with Dsa? Well, remember that Dsa is basically based off of discrete logs. So our public key is some g to the x mod p, where x is the private key that should be secret. So again, if two hosts share exactly the same public key, they both know the private key of the other, assuming they have sort of the same domain parameters and the same y. But Dsa actually has a much more interesting property in terms of key sharing and randomness, which is that, as I mentioned in the first talk, Dsa signatures are randomized. So you have to compute this random nonce k, which is in red here. And if this Dsa nonce is known for one signature, then you can easily compute the long-term private key for a Dsa key. So if I know this value k, then given the signature pair, which is like R and S1, then I can compute k inverse mod q and then just solve for x in this equation from the signature in the message, and then get x, which is my long-term private key. So this is a somewhat fascinating property for a signature scheme to have. We can go one step further, and maybe we don't know k, but maybe if someone accidentally signs two distinct messages using the same nonce k, then from the signatures of those two messages, I can compute k just using this equation here. So I just subtract the signatures, and then I can solve for k inverse because all of my arithmetic is mod q. This is easy. Then once I have k, then I can use the equation, just the definition of the signature, in order to compute the private key. So if you ever screw up randomness in DSA signatures ever. If you ever sign with the same nonce for 2 signatures, then your key is compromised forever. So, of course, after I've given all this sort of alarmist speech about how terrible it would be if we screwed up randomness in these crypto systems, you can imagine sort of, well, should we actually be seeing these in the wild? Is it the case that, you know, if we have, for the key sizes that people actually use, do we expect to see these kinds of collisions? So, you know, mental experiment here, collect a whole bunch of RSA moduli, compute the GCDs of each pair of RSA moduli. Do we expect to find non-trivial common divisors? And the answer is no. So we know how to do this analysis. The prime number theorem tells us how many 512-bit primes say there are in the universe. It's essentially like 512 over, or 2 to the 512 over log 512, plus or minus, well, with some constants in there. The number is approximately 10 to the 150. Then we're asking essentially for a birthday bound analysis. So the birthday bound tells us that the probability that there's some collision, we have m moduli, each modulus has 2 primes. So what's the probability if we have m of these and each one has 2 primes that we get some collision after collecting m? This is the bound. And essentially it says that nothing happens until the number of moduli approaches approximately square root of the number of primes. So I have plotted the probability of a collision here for you with some waypoints along the way. It is essentially 0 or astronomically close to 0 until we get pretty close to the number of atoms in the universe, at which point it pretty quickly jumps to 1. So this means that for any size of number of keys that we would actually be able to store in a reasonable way, the probability that we should see a collision if all of these keys were generated uniformly at random is essentially 0. This does imply that if for some reason we wanted to have like a public key infrastructure for an Internet of Things that encompasses every single atom in the universe, then we might want to move away from 1024-bit RSA. But until that point, we're okay. So continuing with our little mental experiment, if for some reason, despite the fact that this experiment is almost certain to fail, if we want to carry ahead and for some reason compute a bunch of pairwise GCDs anyway, how would we actually accomplish this task? So the sort of naive way to compute the pairwise GCDs of a whole bunch of RSA moduli would be to, you know, for modulus I, modulus j, compute GCD of I and j. This is a quadratic time algorithm, and the number of pairs that we would need to do this for all of the RSA data sets that that I enumerated in the beginning. Well, we had about 14 million keys, so we have 14 million choose 2 pairs, and each GCD would take, say, about 15 microseconds. And that translates to about 1,100 years of computational time, which is not out of the question if you're willing to spin up like a really big cluster. But we didn't really have access to that much computing power, and we didn't want to spend that much time. So this is not what we really want to do. It turns out that there's a much more efficient way to do this calculation, which we did by adapting an efficient algorithm, which is due to Dan Bernstein. So this is a sort of picture of the way the algorithm works. It has a couple of stages. You start with all of your RSA moduli, n1, n2, n3, n4, and so on. Then you compute the product of all of these moduli in a binary tree. This balances the time of each multiplication. Then once you have this gigantic product, then you mod out by the squares of all of the nodes in this product tree that you just computed. Your end goal here is to get the value, say, n1, n2, n3, n4 mod n1 squared. then you can divide by n1, so that gives you the value n2, n3, n4 mod n1. And then once we have that, then we can just compute the GCD of this fairly small number, which is the size of n1, but is actually n1, n2, n3, or n2, n3, n4 mod n1. The GCD of that with n1 is actually, because the first step of Euclid's algorithm is to compute mods, it's exactly the same as the GCD of n2, n3, n4, and n1. So this value will tell us if n1 has any non-trivial common divisors with any of the other keys. And because we've been cleverly computing everything in binary trees, instead of taking quadratic time in the number of keys, this algorithm will essentially take mn polylog mn time for m n-bit integers. And that means that in practice, for the data sets that we collected, this algorithm finishes in a few hours. For the SSL and SSH keys together, it took, I think, an hour and a half to finish on one Amazon EC2 instance, which corresponds to $5 of EC2 time. And an implementation of this algorithm in C, which is reasonably fast, but not, sort of the end of the story if you want to improve it, is available at factorable.net if you want to play with this stuff at home. So with all of that introduction done, what actually does happen when we GCD all of the keys? And after doing this calculation for some of the data sets that I mentioned, you find the private keys for 64,000 HTTPS servers, which is about 0.5% of all of the HTTPS servers out there. About 2,500 SSH servers, which is about 0.03% of all of the SSH servers out there. 2 PGP users, and you actually find a few hundred invalid keys due to what looks like some bug, and 103 poor Taiwanese citizens. What happens if we look for repeated DSA nonces? So in the case of SSH, SSH's usage of DSA is handy because if we collect a bunch of SSH handshakes, we get signatures along with the public keys, so we can just look for collisions. And looking for collisions among the signatures gave us the private keys for 105,000, or about 1% of all of the SSH DSA servers on the internet. And it also gave us, well, it gave some other people the private keys for 133 Bitcoin addresses. So what if we, I mean, the easiest thing to look at, which I didn't start with, is what happens if you look for repeated keys in some of these key databases. And it turns out that repeated keys are shockingly common on the internet. So more than 60% of HTTPS and SSH servers served non-unique public keys. But it turns out that most of these are not actually vulnerabilities. There are a lot of valid reasons that are very common that are not vulnerabilities that hosts share keys. Some of the most common ones are shared hosting situations, virtual hosting. A single organization might register many domain names with exactly the same key. Google has like google.everyTLD, and they use the same keys for a lot of these. And we also see a lot of, for example, expired certificates that are just renewed with the same key. Once you sort of eliminate all of these valid-looking reasons for sharing keys, you find a lot of common and unwise reasons to share keys. By far the most common one is default certificates and keys. So various kinds of devices that just come with some kind of certificate just baked into the firmware that has some fixed key. And after looking through those, we saw what appeared to be apparent entropy problems in key generation. So some of the numbers for HTTPS and SSH, the number of hosts on the internet that are serving default certificates or keys for HTTPS is something like 670,000 hosts, which is about 5% of the keys. This is a massive lower bound because we characterize these by hand. And so if you could somehow do this automatically, the number would almost surely be much higher. And for SSH, we had a harder time telling the difference between default, default host keys and low entropy keys, but a lower bound for the number of hosts sharing keys is something like 1 million, or about 10% of the SSH hosts out there. Sorry. And this is a massive lower bound. It comes from just looking through, say, the 50 or 100 most common SSH keys out there and characterizing them. And for HTTPS, a lower bound for the number of repeated keys that are due to entropy issues is at least 40,000 hosts, or about 0.3% of all of the hosts on the internet. If you do the experiment of, for example, looking through the 50 most common SSH keys, so this is a plot for Rsa keys, this is something of what you find. This is me characterizing by hand whether these keys appeared to be associated with a hosting provider or device, or with something else. So in the red, these are all the keys that sort of were obviously generated by some kind of device. You just connect to it and it says, hello, I am a router. In the blue are all of the keys that were obviously associated with some kind of hosting provider, where they may have thousands and thousands of IP addresses, but they only have sort of one, they only serve one hosting key. And we're assuming that this is not a vulnerability, that the clients don't actually have access to the private keys when they connect. And then there's a very small number of keys that don't, that are highly repeated, that don't fall into one of these explanations. So in this plot, the most commonly repeated SSH key was a hosting provider. It belongs to, it was served on about 200,000 IP addresses belonging to the hosting provider Verio. If we go through and look at all of the HTTPS certificates that are that we factored, what is going on there? Well, fortunately, the certificates have a large amount of information about how they were generated, who they belong to, giving us clues to what might have happened. And in the 60,000 factored certificates, only 2 of them were signed by a certificate authority. This is in contrast to about a third of the HTTPS certificates overall that we collected were signed by a certificate authority. So something different is going on with these keys. If you look at the subject information for the certificates that we were able to factor, you see something that looks like this, where, okay, so the CN equals self-signed, CN equals system generated, CN equals something that looks like a serial number, something that identifies itself as some kind of router, some other kind of router, random IP address, random printer. So what we're seeing are what looks like auto-generated certificates from various kinds of network devices. And so in attributing the vulnerabilities in SSL and SSH, it was clear upon just immediately looking at the data that nearly all of these were obviously due to some kind of implementation problem. And sort of the available evidence, for example, the subject or the subjects of the certificates connecting to the addresses that were serving these weak keys, almost all of them were very obviously some kind of network device. And we identified many of the devices that were serving the most common certificates, and we saw basically all of the biggest names in the industry. So Juniper network security devices, Cisco routers, server management cards from basically every single manufacturer who has ever made one of these things. some industrial grade firewalls, printers, projectors. The list sort of goes on and on. Every single little kind of headless embedded network device that you could imagine, we saw some example of it out there serving factorable keys. So why are we seeing these things? So the explanation sort of lies in how these little devices are generating their crypto keys. I mean, how if you're a little Wi-Fi router, how are you generating your crypto keys? Well, you know, in order for the keys to be secure, they need to be random. In order to generate random keys, we need a source of randomness. Where does it come from? Well, if I'm my little router, I am going to generate my crypto keys using some software, probably say Openssl or something similar. So the crypto application will have some pseudorandom number generator that it will use to produce the randomness to generate these keys. But where is the seed coming from for the pseudorandom number generator in the application? Well, it comes from the only place that it can, which is the operating system. Generally, so the operating system maintains some entropy pool of randomness, and then it might also query things like the time or the PID in addition. And so where is the operating system getting its entropy from? It gets it from, in Linux, basically the only sources that it's guaranteed to, which is sort of external devices that interact with the outside world. For example, keyboard timings, mouse movements, hard drive timings, and things like network interrupts. Although there was a period of time when Linux stopped collecting device interrupts. And so the only sources of entropy were the first three. So for these little network devices that we were seeing, why were they generating keys with such bad randomness problems? So the hypothesis that we were working with was that these devices were automatically generating the crypto keys on first boot. So I get a Wi-Fi router, I take it home, I take it out of the box, I plug it in, it boots up for the first time, it starts its SSH process. The SSH process says, ha, I don't have a host key, I will generate a host key now. That's one of the very first things that it does the very first time that it gets booted up. And so problem number one is that for these kind of low resource, tiny little computing devices, they may lack all of the entropy sources that the operating system is assuming that they have access to. So your little Wi-Fi router doesn't have a keyboard, it doesn't have a mouse, it probably doesn't even have a hard drive. And it might not be connected to the network yet. And problem number two for these little devices is that even if they do have access to some entropy, the operating system might not have actually incorporated any of the entropy that it does have access to into its entropy pool when it's queried by the application software. And one of the reasons for this is that, for example, Linux, in order to protect against the attack, where an attacker carefully monitors each of the entropy sources that are being incorporated into the entropy pool and sort of tracks the state of the entropy pool as it's added. In order to protect against this, it collects the input in a separate pool and only adds it to the output pool when it's reached a certain threshold. And so until the output pool has reached a certain threshold, the output of the random number generator might be deterministic. And this we called a boot time entropy hole, and we experimentally verified that Linux actually had this behavior in practice. This has actually been fixed since. But this is one of the major contributing factors to these entropy problems that we're seeing. So why I want to discuss a little bit the design of the random number generators in Linux in order to understand from a usability perspective why we had such, why we found such problems. So Linux provides, as most of you probably know, 2 random number generators available to users. There's dev-random, which is guaranteed to provide high quality randomness, and it will block if insufficient entropy is available. And because sometimes you don't want your entropy source to block, it also provides dev-random, which provides no guarantees on the quality of the output, but it is guaranteed to never block. And if you read the man page for random, it says, as a general rule, dev-random should be used for everything except long-lived GPG, SSL, and SSH keys. So you have exactly one guess as to which of these people were using to generate their long-lived SSL and SSH keys. Any guesses? And so yes, everyone was using dev-random. And the reason is that this conservative blocking behavior of random is actually a usability problem. So on a little Wi-Fi router, if you try to use dev-random to generate your SSH keys, it may never provide any output at all because you don't have any of the sources of randomness that it has access to. And so the hapless developer who's constructing this device would, try to boot up the device and say, well, it's not booting. What's the problem? Well, oh, the difference between dev-random, dev-random is like the difference between information theoretically secure crypto and computationally secure crypto. Therefore, it's only of academic interest. Therefore, the reasonable solution is to use dev-random to generate your crypto keys. And this is what nearly everyone does. And here's a representative quote from one of the pieces of software that we looked at. So this is from Dropbear, which is a, I guess, lightweight SSH implementation, which is commonly used in a lot of these embedded devices. So it says, we'll use dev-random by default since dev-random is too much hassle. If system developers aren't keeping seeds between boots nor getting any entropy from somewhere, it's their own fault. And then it goes on to define their randomness source as dev-random. I mean, this is not particularly to pick on these people. This is just representative. This is what everyone does. Okay, so we've established that if you are using Linux to generate your crypto keys with some standard libraries, when you are generating your keys and you query the operating system for a random seed, you might get a predictable value of the random seed at first boot on some resource-constrained devices. And so if you think about, well, what does this mean for the crypto keys? If you think about, well, what's the easiest way to generate an RSA key? Well, you can imagine sort of, this is just pseudocode here. I'm, say, seeding my pseudo-random number generator from the operating system. I use that pseudo-random number generator to generate 2 random primes, P and Q. I multiply them together to get N. If I'm getting a deterministic seed from the operating system, then I should always see the same value of N being generated by the devices. And as I mentioned, we do see an enormous number of shared keys in practice. And of course, these repeated keys, due to entropy problems, are a sign that the implementation might be vulnerable to a much more targeted attack, where you just enumerate all of the possible seeds from for the pseudo-random number generator and just generate all of the possible keys that could be generated on that particular device. But this doesn't explain why we saw all of these factorable keys, these keys that were sharing exactly one prime factor in common, but not both. Because basically, I mean, our pseudo-random number generators are pretty good at this point. Those are not the things that are going to be generating collisions. So the reason in many cases that we saw factorable keys being generated is because the implementation pattern looks something more like this, where you seed your pseudorandom number generator, but then over the course of generating your keys, you are continuously adding more entropy into the application's entropy pool. And so, you might generate your first prime and then add some more randomness and then generate your second prime. And where is this entropy coming from? Well, OpenSSL is every time you query the OpenSSL entropy pool for a random big num, it adds the current time in seconds to the entropy pool. Now, this doesn't sound like a very good source of entropy, because sort of the model that we're working with is that these devices, they're basically, you boot up a couple of identical devices, they have exactly the same clock time, which is probably Unix time 0. They will be in exactly the same state. Their dev random states are exactly the same, and everything should be exactly the same. So where is this entropy coming from? Well, it turns out that due to clock drift and like slight asynchronicities in different devices operating, maybe the temperature, maybe something else, maybe small amounts of interrupts or something non-deterministic in the execution, can result in slight differences in the clock time, even for identical devices. And this clock drift provides just enough entropy that in many cases you can generate factorable keys of the kind that we saw. So here's sort of an example of two devices. They boot up, they have exactly the same clock time, they have exactly the same dev random state, they start generating their keys in exactly the same state, but one of them is running just slightly slower than the other one. And so as they tick, say they're generating P and it's time 0, but then the clock tick happens on slightly different execution cycles in the two keys. And at this point, say during the generation of Q, because the clock ticks happened on different cycles, when they query some entropy out of the entropy pool, they're on slightly, the number that's added is slightly different in different stages, and then from there on, the key generation process diverges. Yeah?
If they would use a device ID to figure out something for the pseudorandom number generator for the first one, so then would it follow this attack? Because then the first one would be different.
Yeah, it should be different. Yeah, if you have different seeds when you start generating the keys, then you should just see completely different both P and Q. And so the interesting thing about this is that the first prime that's generated is identical, and if you happen to diverge sometime in the generation of the second prime, then you get the same first prime, different second prime, and then you get the factorable keys. So we experimentally verified that OpenSSL can generate factorable keys in exactly the situation where you fix all of the entropy sources except for the addition of the time in seconds, and sort of simulate a resource-constrained device that has nothing else running, just this. So why do we see things like the weak DSA signatures? So the DSA signatures are interesting because you might think that sort of even if at very first boot we've got some entropy issues, by the time these devices are actually running in practice, they've been on for a while, they've had time to get entropy from their environment, their states should have diverged. We shouldn't be seeing these kinds of collisions. And what was happening in many cases was sort of a combination of problems. So step one is that, say you have your little router with, it's going to generate its SSH key on first boot. Because of the entropy problems we identified, you might have a whole bunch of these routers all generate exactly the same public key at boot. And then when the SSH process starts, it seeds itself once from the operating system and uses that to seed a deterministic pseudorandom number generator, which then is used to generate the signature nonce for the rest of runtime. So even though the operating system's entropy pool might have diverged in state at this point, because the application's entropy pool was seeded at boot, it still has the same problem that it was seeded with a deterministic value. So if we then have a huge number of these devices that are all sharing exactly the same public key, and we're just scanning the entire internet collecting one signature from each device, if we happen to hit 2 of these devices that have managed to generate exactly the same public key and have their deterministic PRNG states for generating the nonces be in the same state, then we will get a collision of nonces and then be able to compute the private key for, that both of these devices are using. And in practice, we saw tens of thousands of Wi-Fi routers that were all serving, say, exactly the same public key. And so all it took was one collision from 2 of these devices, and then the private keys for all 10,000 of these devices would be compromised. So here's a sort of picture of the deterministic sequence of values that 2 routers might be producing, and the collision that we would get. So this is an example of how runtime problems at first boot can, through sort of the design of the application software, persist into sort of runtime, even when the state, even when the operating system is trying its best to get entropy right. Yeah?
It should be selected for a much wider range of possible values, and then the probability of conflict or collision may drop, which is also a question about the previous slide. Why did they use the time in seconds or not in milliseconds or in microseconds? And then the chance for a collision should be much lower.
So my understanding of OpenSSL is that a lot of the design choices that are made are in order to make it as interoperable as possible. And so maybe it's using the time in seconds because that's the only thing that can be guaranteed to exist on all of these platforms that it's trying to run on. If you look at the code for where it's seeding the random number generator, it has all of these conditions of like, if random exists, if urandom exists, if srandom exists, if none of these things exist, I'm going to do something really exotic. It just has like all of these very complicated conditions. And so I find adding the current time in seconds to be a very strange choice, but it's one that they're sticking with. And their response has been, well, you know, the operating system needs to get their random seed correct, and then everything will be fine. In this case, these little values, this is just like an illustration. This is not the actual values that they're doing. Of course, they're generating, you know, much larger cryptographically secure sized values. The problem here is that it doesn't matter how big they are. It's just that it's a deterministic sequence. So the problem is that we have this deterministic sequence of values that's being produced. And of course, one thing that's interesting about this is that DSA could have been designed in a way so that the nonce was deterministic. You can generate it, say, as a MAC of like the message and some key, and they chose not to do this for some reason. But having designed DSA that way would have completely eliminated all of these. Let's see, you want the message and your private key. And if you use those deterministically to generate your nonce, then you're secure. And actually, Dropbear actually had code to do this, and it was off by default. And that resulted in generating a lot of insecure signatures when you had randomness problems of this kind. So what's going on with these Taiwanese keys? Just to recall, we factored 103 keys out of something like 3 million by computing GCDs. If you take a look at the most commonly repeated factors, this is the most common shared factor of these keys. which appears 46 times among the keys that were factored. It consists of 2 top bits are set, a whole bunch of zeros, and then some bottom bits that are non-zero. And this turns out to be the next prime after 2 to the 511 plus 2 to the 510. So set the 2 top bits, increment to next prime. There's our prime factor. The next most common factor in the list was repeated 7 times. And here's the hex value. And it has this sort of interesting repeating structure, but it's like not quite periodic. And then there's like a little bit at the end. And again, the 2 top bits are set. And basically, many of the other commonly shared factors in this data set had these kinds of patterns. So what is going on with these sort of but not quite periodic patterns here? You see, it's almost periodic, but there's some problems. So taking a look at the way that this appears to be generated, well, step 1, take 32-bit words and swap each 16-bit word. Having done that and sort of realigning, then we get a perfectly periodic sequence, except for like the 2 top bits that we set, and then the bits that are due to sort of presumably incrementing to the next prime at the least significant bits. Looking at this structure, the commonly repeated factors that we saw all had patterns of period 1, 3, 5, or 7. So the hypothesis of the way that these particularly weak primes were being generated is that the key generation process looks something like this. Choose a bit pattern of length 1, 3, 5, or 7. Repeat it to cover 512 bits. For each 32-bit word, swap the upper and lower 16 bits. Fix the 2 most significant bits to 1, and then find the next prime, which is greater or equal to this number. This suggests a further cryptanalysis of these keys, which is, well, we didn't see every possible pattern, so let's enumerate all the possible primes that could have been generated using this. And there was something like 162 distinct primes in that case, and just trying trial division with all of these keys gave us the factorizations to 18 more keys belonging to poor Taiwanese citizens. And extending this to patterns of length 9 gave us the factorizations for 4 more keys. So the big question here, I mean, I spent a lot of time talking about the random number generation problems in these sort of like low-powered Wi-Fi routers running Linux and the like. In this case, we factored far fewer keys, but in some sense, the problems seem much more severe because these are smart cards that are being issued by a government. They give you a legally binding identification. And if you look at the sort of literature that the government was passing out, they were claiming to follow the most stringent standards in for cryptographic hardware security. So the best practices in hardware random number generation sort of require, for example, the designers, you need to characterize the entropy generated by your circuits. You need to test the signal from the entropy source at runtime. You need to post-process this signal by running the output through some cryptographic hash function. And just by staring at the prime factors that these keys were generating, or the prime factors of the keys that these cards were generating, it's very clear that these particular cards were doing none of these things. They were not testing for entropy problems. They were not running them through the output through a hash function, even though it was claimed in the public literature that these cards were FIPS compliant. So we can hypothesize a failure mode of these cards, which is that often in hardware random number generation, you use something like a ring oscillator, and you want to have sort of a chaotic interaction between a number of these circuits, and this should produce good, reliable hardware random number generation. But if you have these oscillating circuits, they can get stuck in a particular configuration. And maybe when they get stuck, they might output just a looping sequence of bits. And then the particular card software determines this pattern of interchanging bits. And yeah?
Do the Taiwanese have any revocation mechanisms for these IDs?
They have, yes. So they can revoke the certificates, and people can regenerate their keys. Yeah. So if we hypothesize that these particular cards had some failure mode where they were getting stuck and outputting deterministic output from the hardware, and then failing to do any kind of post-processing on the random number generator output, then you might see this kind of patterns arising in practice. In terms of the PGP keys, this is, I think, it remains an unsolved mystery because PGP is very careful about how they do their random number generation. They're not using dev-urandom. So why did we see two users have PGP keys that share one prime factor in common? I don't know this, and the Leinster et al. Paper has no explanation for this. The keys that were affected were both more than 10 years old. Both of the users were in German-speaking countries. I don't know what happened. If someone does, that might be interesting.
Could it be a hoax of some sort?
No, these were real keys. In the Leinster paper, they apparently contacted one of the users who was shocked to discover that his key was not secure. So I don't know what the story is. In terms of Bitcoin, this comes from a couple of analyses. The hypothesis of what was resulting in the failure of a very small number of Bitcoin addresses to give secure signatures all the time was that these keys were associated with uncommon or test implementations. And this was apparently confirmed for at least one implementation that the repeated nonces were a testing value. And this is a plot of the interactions between the Bitcoin addresses that were affected. So red is vulnerable keys. And you can see that like a large number of them, like these all clearly have something in common. There's something going on here. And then there's a couple more sort of connected components that are probably all related to each other. And in January, none of these vulnerable addresses contained any Bitcoin value. So what did our disclosure process actually look like? For the HTTPS and SSH vulnerabilities, which were extremely widespread, there were an enormous number of companies' products that were affected. We wrote disclosures to 61 companies, and it's basically everyone who's ever produced any kind of hardware. And of these 61 companies that we tried to contact, 13 of them actually had some kind of security team contact information available. So in all the other cases, we just had to guess, like how are we going to contact this company? We received responses from 28 of these companies, so less than half of them ever got back to us in any capacity whatsoever. 13 of them in the past year and a half have told us that they fixed the problem. 5 have informed us of some kind of publicly available security advisory about these random number generation issues. And we coordinated the disclosure through US CERT and ICS CERT, the Industrial Control Systems CERT, and JP CERT for one company. I think notably the Linux kernel was patched last summer after we contacted them. This was actually very impressive. I think we emailed the kernel security team, and within like half an hour we had a response from the in response to these problems, they made several changes in the way that entropy processing happens, especially on first boot. I think they added interrupts back in many cases, and they're more generous about how entropy is incorporated into the output pools in first boot in order to try to mitigate this problem. They also add things like the MAC address to the entropy pool that should at least, this is not a cryptographically good source of randomness, but it should keep these kinds of GCD problems from appearing in the future. And actually some numbers from follow-up work by Alex and his students. Since August 2012, when we published our paper, there's been a 20% decrease in the number of hosts that are serving factorable RSA keys. So this is some evidence that hopefully disclosure of problems actually does some good, that these are fixed and the new keys that are being generated are less vulnerable than before. So the disclosure process for the Taiwanese vulnerabilities, we disclosed the vulnerability to the Taiwan Ministry of the Interior, and they have replaced cards for users that are directly impacted by the GCD vulnerabilities, and they have revoked the certificates on the public databases. And they have also promised to replace cards from the particular vulnerable batch that they say is responsible for generating these weak keys. So I'm going to finish up here with a brief gallery of horrors of some of the things that we found when looking through these key databases. So first, I mean, one of the most infamous entropy problems that has happened in recent history, the Debian random number generation failures. So in 2008, it was discovered that the Debian package of Openssl, someone had unwittingly commented out the line that actually added entropy from the entropy pool into, actually added entropy from inputs into the entropy pool. And this was because a similar line was causing some memory analysis errors. And so this was sort of widely disclosed, and there was a massive effort to replace the weak keys that were served on Debian machines. Because due to this bug, I think there was something like 16 bits of entropy on any given architecture, which means that just lists of all of the possible SSL and SSH keys that could have been generated on a Debian machine between 2006 and 2008 were just immediately published. So using our scan data, we're actually able to measure the number of hosts that are still affected by this problem. And last year, Debian weak keys were being served on 4,000, or about 0.03% of HTTPS hosts, which is more than it should be, but not as bad as you might think. But actually, a much larger number of SSH hosts are still vulnerable to Debian weak keys. And one might hypothesize that in the case of HTTPS, you have very good contact information for the servers that are responsible. And because of things like the SSL Observatory, people have made a great effort to contact all of the hosts that are serving Debian weak keys. Whereas SSH, as far as we know, we were the first to actually scan for all of the SSH host keys. And so perhaps nobody has gone through and tried to tell all of these hosts that they need to change their keys. Another example of somewhat alarming problems that we found. So I don't know how many of you recognize this Ssl certificate. This is a certificate for snakeoil.dom, and it has contact info, Snake Desert and Snake Town. This is the default certificate if you install a new Apache installation and you turn on SSL. So we saw, unsurprisingly, a very, very large number of these certificates out there, which is fine because, you know, obviously this is not serving anything particularly secure. But what we saw that was much more alarming is that some number of poor websites had somehow managed to take the key that was included in the Apache default certificate and put it into their own certificate with their own domain name and own contact information and get this signed by a certificate authority and serve it on their real website that they were actually using for important things. This tells us a couple of things. One is that users will somehow manage to mess up your instructions no matter what you do. And thing number two is that clearly, at least last year, certificate authorities were not checking anything. They were perfectly happy to sign certificates containing these keys that were just, completely insecure, included in, every installation of Apache ever. So that's alarming. This is a plot of the prime factors that were generated by the IBM Remote Supervisor Adapter 2 and Blade Center Management Module. These are sort of lights out management cards sold by IBM. So the way that this plot works is that each column here corresponds to a distinct prime factor, and then each stacked block here tells us the number of distinct moduli that shared that prime factor. So the way that these keys, sort of just from the outset, had apparently been generated is there are 9 possible primes. Choose 2 of them uniformly at random, multiply them together, that is your RSA key. So, what?
What is it used for?
These are little cards that you can plug into your servers to remotely administer them, to reboot them and whatnot. So you SSH into your card, or you use the HTTPS interface to administer your server. This is a case of a random number generation problem that is not the Linux or similar sort of boot time entropy problems. This was actually just due to a straight up bug in their key generation software. Apparently they forgot to dereference a pointer, and so the randomness was just the top sum bits of whatever pointer that they were using to point to their entropy. So it is incredible that something like this could exist in the wild and be sold and nobody noticed until last year. Some other problems, well, these keys look a whole lot like the Taiwanese keys, but these are being served by SSH servers. And I don't know what software is responsible for this, because this doesn't look like, say, the keys that OpenSSH is generating. Here are some other prime factors of some HTTPS keys that we found. And basically, these collections of prime factors, they share way too many bits in common in the most significant fraction of the bits of the prime factors. I don't know what kind of implementation pattern might be generating this. Maybe they have some entropy source that they're reading really sort of very slowly and it diverges. Maybe they're picking some memory address and that's their entire entropy source, and so it changes slightly. Maybe they're incrementing to next prime somehow. I don't know what is responsible for this. So what are the sort of practical mitigations for these kinds of problems? For developers and manufacturers, I think the biggest one is defense in depth. You want to make sure to protect against the kinds of cascading catastrophic failures that we've seen in many of these cases. You want to, when generating keys, you want to test the quality of your output, you want to post-process all of the inputs that you get, you want to use multiple sources of randomness. For these kinds of small resource-constrained devices, a solution is to collect entropy more aggressively on boot and add hardware sources of entropy. For example, the new Intel chips that contain a hardware random number generator, and then they have the read random instruction. Although apparently many pieces of software are now using the output of these Intel chips without any further processing. So that seems perhaps unwise. For these kinds of mass-produced devices with entropy problems, one solution that should be fairly straightforward is that these devices could be seeded with entropy at the factory. At the same time as you are putting a unique MAC address into each device, you can add a unique random seed that has good entropy into each device. And then as it runs, it should, even if it has very poor entropy collection, it should still be able to have a suitable source of entropy. And finally, a reasonable solution in practice is that if you have to generate a crypto key, perhaps the first time that you boot up is not the best time to generate your crypto key. If you run for a while before generating your keys, this gives you time to connect to the network, get further sources of entropy, have user interaction, and then perhaps have more entropy to generate good crypto keys. So you could generate keys on first use rather than on first boot. Certificate authorities are in a good position to be testing for these kinds of problems. They can detect repeated factorable and other kinds of weak keys from their sort of God's eye view of the internet. I don't know if any of them are doing so now. They clearly weren't last year, although there was quite a bit of interest in this work. For users, there's not a lot of protections. You can check against databases of known weak keys. We have a certificate checker on our website at factorable.net, and a good protection against some of these problems is to replace default certificates if they are built into devices that you care about. So what are the lessons here? From a systems perspective, we got sort of these new insights from taking a macroscopic view of crypto practice. We started by thinking about things from the perspective of the, say, Rsa keys that we were finding in the wild and what happens if you compute GCDs, but actually what we found in the case of Linux was a much broader problem in random number generation that would affect every single thing that any of these devices is doing at first boot. So the crypto problems were actually just sort of the canary in the coal mine of these much broader, more serious problems that a dedicated attacker could try to exploit. And one of the things that this tells us is that cryptographic entropy is very hard to get right, and we still have a lot of work to do in practice in terms of getting it to be absolutely secure in all cases. From a cryptographic perspective, a useful design question is, how can you design crypto systems that are resilient to this kind of failure? In particular, for random number generation problems, there's been some work in the academic crypto community in producing hedged public key crypto systems, which try to take advantage of any entropy that they have access to, for example, from another party in a cryptographic computation in order to get entropy. In terms of the systems in practice, this is a useful, I think, design criterion. So as I mentioned before, DSA was not, clearly not designed thinking about this problem. And so this is how we ended up with such catastrophic problems with DSA keys when the nonces were generated using port randomness. And the keys could have been, DSA could have been designed in such a way that if the nonces were deterministic from the private key and the message, then it would have been completely resilient to this kind of problem. From a theoretical perspective, there's a lot of interesting algorithmic problems of essentially, if you have a gigantic database of cryptographic keys, we only looked at some of the most elementary possible things that could go wrong. There's a lot of other slightly more subtle things that can go wrong, and the only question is how can you actually efficiently do this kind of computation for the size of key data sets that we have. So even with 5 million keys, a quadratic algorithm is not going to be efficient enough to actually terminate. So how do you look for these kinds of subtle problems? I'll do a little bit more of that in the next talk. So the summary of this talk is if you have bad randomness and you have bad keys. And in the next lecture, I will do some more math and we will factor some more keys. So thank you.